In this video, we're going to look at naming simple single transformations. We've got 4 different types of transformations. We've got translations, we've got rotations, we've got reflections, and enlargements. In the video, what we're not going to do is a combination of 2 different types of transformations. Also, when we look at our enlargements, we're simply going to state the scale factor of the enlargement rather than any centre of enlargement. So let's start off by looking at the 4 different transformations. Once we've done that, we're going to work individually on naming each of the transformations that take a certain shape to another. The first type we've got are translations. If we translate a shape, we simply move it. So there's no alteration in its size, it's not flipped over, it's not turned round, it's simply moved. So when you're playing chess, for example, or drafts, you can translate one of the pieces. You can move it forwards, you can move it across. If we think it's a translation and we think the shape has simply been moved, we write down that it's a translation and then we write the vector. When we work through this question, we will look at the vectors we use to translate a shape. The next type we have are rotations. Rotation means to turn a shape. So if you think that shape has been turned, so it's the same size, but you think that it's been rotated about a point, you will say that it's a rotation. You can't write it's been turned, you must state that it's a rotation. When we describe fully a single transformation and it's a rotation, we need the centre of rotation. So the centre of rotation. We need the direction of rotation. And we need direction of rotation, and we need the angle of rotation. So angle of rotation. These are the 4 pieces of information we must give. So when we look at the centre of rotation, for example here, from C to B, we can say that the centre is going to be 2, 1. The x-coordinate is 2, the y-coordinate is 1. We can then look at the direction of rotation, so it's either clockwise or anti-clockwise. And then we can look at the angle of rotation. Usually it's 90, 180 or 270 degrees. The next type we've got are reflections. So with reflections, these have been mirrored in a given line. So we would need to state that it's a reflection. So for example now, A and C, well, C is a reflection of A. If we think it's a reflection, we need to state the equation of the line that it's being reflected in. So equation of line of reflection. So let's just put this in. So with a reflection, like a rotation, the size has not changed. The only time a size will change is if it's an enlargement. So with this now, we're looking at shapes that may, especially if they're these little triangles, be flipped over. They're flipped about a certain line. What we'll do when we come on to these is looking at naming the equation of the line. So we might say the shape A to shape C has been reflected in the line y is equal to 1, x is equal to 3, y is equal to x, the x-axis, the y-axis. Let's now look at the last type of transformations, and they are enlargements. We're going to look at basic enlargements. If we think the shape has got bigger or smaller, we state that it's an enlargement, and we need to state the scale factor of enlargement. So these are the things that you're going to write down. We're going to work through the questions and name them. I think it's important to state at this point, when you're asked to name fully a single transformation, you might have an example of where it could be a translation, a reflection, or a rotation. They will all be equally valid. You just have to decide on one and list out fully what you think has happened to it. So let's go ahead and look at some. All of these, generally speaking, will be translations. What we'll do is look at them as translations and then look at some alternative transformations that we could state for each. So it says state fully the single transformation. Often it will say a single transformation, so you have the opportunity to choose something different to a translation. So translation, we want to know what maps shape A to B. Maps mean just move it. So what takes me from A to B? What I need to state is that this is a translation. It has been moved. So a translation, or you can say the shape has been translated. What we now need is the vector that moves A to B. Vectors just tell us about the movement of an object. We write a vector like so. I'm going to write some vectors just here, and I'll give you some examples. 1, 3. -2, 7. 1, -3. Let's go for -5, -4. Let's go for 0, 6. The top number tells us now what it's done in terms of the x-coordinate. So the top number is the x-coordinate, the bottom number is the y-coordinate. If the top number is positive, it's moved right. If the top number is negative, it's moved left. If the bottom number is positive, it's moved up. If it's negative, it's moved down. So on this first one, we're going to move right by 1 and up by 3. On the second one, we move left by 2 and up by 7. On the third one, we move right by 1 and down by 3. On this one, we move left by 5 and down by 4. On this one, we don't move left or right, and we simply go up by 6. So if we look now from A to B, well, A has moved left 1 and up 1. If you want to do it with a pen, you can do. You can simply pick this point up and go 1, 1. So it goes left 1, up 1. So my vector is simply going to be now left 1, up 1. So left 1 is -1 and up 1 is +1. So it's a translation, and that is the vector. Whilst we're here, that particular transformation may not have been a translation if we didn't want it to be. It could have been a reflection, and the reflection would be the mirror line just here. The issue with this, though, is that we would need to find the equation of this line, which is significantly harder than saying that it's just been translated. That is an option. Alternatively, what you could have done is use your tracing paper, and I'll show you how to do this. It's going to be slightly more challenging for me to do it. We could have used our tracing paper, put now our square around A on the tracing paper. I always draw a north line, and if we draw a north line and put our pencil on here and rotate it, we could see that that would have become a rotation from A to B. So it could have been a rotation about the point -2, 4, and if we rotated that, we could have worked out now the angle of rotation as well. We will look at rotations as we go, but they are possibilities. So if we now look at 2, well, what we need to do is B to A. Again, this could be a translation because it's simply been moved. B to A is going to be the opposite as A to B. So with B to A, we have moved right 1 and down 1. So it'd be +1, -1, right 1, down 1. Again, you could say that it's a reflection or it's a rotation. It's entirely up to you. A to C, again, we would need to state that this is a translation. You must keep writing it down. I know it sounds boring and I'm banging on about it, but you'll be given 1 mark for stating it's a translation and 1 mark for the vector. So again, A to C, well, that's the same as B to A. It will be a translation, right 1, down 1. If we look at C to B, so again, we write translation. I need to move left 2 and up 2. So -2, +2. Left 2, up 2. If I want to do now E to G, we need to go across by 5. If you're unsure, just count once, twice, 3 times, 4 times, 5 times. So with this one now, let's see what we've got. What's that going to be? E to G. So E to G, again, it's a translation. It's moved right by 5 and it hasn't moved up or down, so we put 0. If we look at G to E, well, G to E is going exactly the other way, so we can say it's a translation, this time -5, 0. What I do like about E and G is that we could have said this is a reflection. I actually think this is nicer as a reflection. and we could say that that is a reflection in the line x is equal to 1. This is the line x is equal to 1. What we have are the points here, 1, 0, we've got 1, 1, we've got 1, 2, we've got 1, 3, we've got 1, 4, and we've got 1, 5. All of the x coordinates here are 1. So we can say that is, so if we wanted to, 6 and 5, we could say now this is a reflection. So reflection in the line, x is equal to 1. If you look at that now, the distance from E to the line is 2 units. The distance from G to the line is 2 units. If you're at home and you stand in the mirror and you're 2 feet away from the mirror, you're going to be 2 feet the other side of the mirror. And that's an important thing, and we'll look more on reflections. So that is an example of a reflection as well as a translation. Lines x is equal to 1, x is equal to 5, and so on and so forth are vertical lines. The lines y is equal to 1, y is equal to 5 are going to be horizontal lines. So that's a nice one just there. A to E, well, let's look at A to E. A to E is a translation. So we've gone 1, 2, 3. So we could say now that A to E is a translation, and the vector we would use is 0, negative 3, as it's gone down by 3. Once, twice, 3 times. If we went from E to A, again, it would be a translation. This time it would be 0, 3, because we're going up 1, 2, 3. What we could have said as well is that this too is a reflection. If I put this line here, this is the line y is equal to 2. So we can see that it's 1 unit away and 1 unit away. This is a line y is equal to 2. Just think of all the points on here. This point is 0, 2, 1, 2. We've got this one, which is 2, 2, 3, 2, 4, 2. The y coordinate of those points on that line are 2. So y is equal to 2. So if you want, you could say the single transformation that maps A to E is either a translation of 0, negative 3, or it's a reflection in the line y is equal to 2. As you can see, these are straightforward. I don't think it's really worth doing the other ones, as we're fairly happy with them. So nice and logical. Part B, draw the shape H such that the translation of A to H is negative 1, negative 2. There is a video on carrying out transformations. What we're doing here is naming them rather than carrying them out. But if we wanted to carry this out, A to H, negative 1, negative 2. So left 1 and down 2, and that would be just here. So let's go ahead and do that. Let's grab that one, and we will put, so left 1 and down 2, H would be just there. So that's what we would have. Again, reasonable. There we go. H is just there. It might then say, name a simple transformation that maps H to B. Again, we could do a translation, or we could reflect it in this line, y is equal to 3. So translation, you move the shape, you state that it's a translation, and you state the vector. Okay. With these ones, we have rotations. As we looked at the start of the video, a rotation turns the shape about a point. So we'll state that it's a rotation. We need the centre of rotation, so centre of rotation. We need now the direction, whether it's anti-clockwise or clockwise. So centre, direction of rotation, and we need the angle of rotation. So angle of rotation. These all need to be stated in your work. So if we look right here, what we've got now is A to B. So we need to state a single transformation. So state fully. Don't just say, oh, it's been turned. It has been rotated. So let's write this in. So this is the first one. So it's a rotation, or it's been rotated, either way. We can say about, and this is the point now, the centre of rotation. We find the coordinates, about 2, 1. X is 2, y is 1. What we now need to state is the direction. So if we think about this, this is going clockwise. A to B is going clockwise. B to A is anti-clockwise. So we can say now that it's clockwise, and we need to state the angle. Usually these are 90, 180 or 270. The easiest way to do this in an exam is to take your tracing paper, trace over the original, I've not got my tracing paper on here, trace over the original shape, put on now a north line, so the north line would go here, pointing north above the shape, and then we would just now take our pen or pencil and rotate the paper. What you'll see is that when you rotate it, it will end up here and the north line will point in that direction. That will be a 90-degree rotation as it's a quarter turn. If it ends up pointing this way, it will be 180 degrees or half a turn. If the arrow ends up pointing this way, it will be 3/4 of a turn or 270 degrees. It's important to also stress that if you're rotating a shape clockwise by 90 degrees, you could say you're rotating it anti-clockwise by 270. So let's just go ahead and put this on. As stated, it's significantly easier to see this if you've got tracing paper. So its rotation is about 2-1, it's clockwise, and it's 90 degrees. B to A. So we're going in the opposite direction. Again, it's a rotation. It's about the same point. So if we take now B to A, it's about 2-1. They're the coordinates. It is anti-clockwise as we're going in the other way, anti-clockwise. And this again is 90 degrees. So we're just coming back down here. Our north line would be pointing now west. Or if you like, if you started at 12 o'clock, it's now pointing at 9 o'clock, which is 90 degrees. Here you're pointing at 9 o'clock and you point at 12 o'clock, that's 90 degrees, it's quarter turn. Okay, A to C. Let's look at A to C. Well, A to C is going to, again, be a rotation. It gets boring doing this each time, but we need to state, we can't say anything but a rotation. It's not being turned. About, we give the coordinates a centre of rotation. Again, this is 2-1, they're the coordinates. We need to say here. Now, with this one, we can say it's either clockwise or anti-clockwise. It doesn't matter. You can even leave this out. About 2-1, 180 degrees. You can see my arrows pointing at 9 o'clock. It will be pointing at 3 o'clock when we get over here. And you could say anti-clockwise or clockwise. So either direction. Because if you think about it, if we stand facing 12 o'clock on a clock and we turn anti-clockwise at 180 degrees, we'll be pointing at 6. If we turn clockwise, we'll be pointing at 6. So with 180 degrees, either direction is clockwise, is anti-clockwise. Okay, A to D. Right, with A to D, what we have here now is a different point of rotation. So again, it's a rotation. So it's rotation, and it's about, or you could say the centre of rotation, you don't have to say about 0, 0, or the origin. This is the centre of rotation, and all we're going to do is simply come downwards. So again, if you want to put your north line just here this time, by the time you rotate it about this point, the line will be pointing in the other direction, so it would have gone from 12 o'clock to 3 o'clock, or it would have gone from 0 degrees to 90 degrees. So we can say this is 90 degrees, and we can say that's clockwise. If you want, you can say that it's 270 anti-clockwise. Let's look at, so we've done A to D. Well, D to A, again, is just the opposite. It will be anti-clockwise 90 degrees about this point. C to B. Well, C to B is going to be 2-1 rotated 90 degrees anti-clockwise. So there we go. Their rotations. You need your 4 things. You need status rotation, you need centre of rotation or point of rotation, the direction of rotation, clockwise or anti-clockwise, and the angle of rotation. As stated, they're either 90, 180, 270. Okay, let's now look at reflections. Reflections have been flipped or mirrored. So when we state now a reflection, we can say now it is a reflection, and then we need to give the line of reflection, or now the mirror line of reflection. So let's go ahead, reflection. That's what we have. Of course, not all of these are necessarily reflections. So for example, you could say that A to B is a rotation at about this point right here. You've just turned it over. Lots will depend on the shape. So for example, a translation could be a reflection as well. It's a case of you choosing and you being a bit more sort of a bit more, what's the word, a bit more flexible. But the more you learn and the more you spot, the more you'll see. So for example, here now we couldn't have A to B as a translation because the shape has changed, the way in which way round it is, or the orientation of it. A to C couldn't be a translation, but B to C could be a translation because it could have just moved from there. We can see that. So let's look at this. With the first one, we need to state fully the single transformation. I'll assume that's a single transformation. Now, I'm going to look at this as a reflection. So we can say now A to B is a reflection, and it's a reflection, and I've got two choices. We can say it's a reflection in the y-axis, or we can say the line x is equal to 0. The y-axis is the line x is equal to 0. The x-axis is the line y is equal to 0. So if I look at the mirror line, as you might have known this before, that is the mirror line. They're bang on this. So if A was here, this wouldn't be the mirror line because A would be 1 unit away and this would be directly on it. So this is the y-axis, or the line x is equal to 0. And it's x is equal to 0 because now this is 0, 0, this is 0, 1, this point here, this is 0, 2, this point is 0, 3, and all of the x coordinates are 0. So that's why we say it's the line x is equal to 0. Generally speaking, you would call that the y-axis, though. So that's the y-axis. Okay, A to C. So what we need to do is find the mirror line. So what line is this symmetric about? Well, all we need to do is put it just there. It's that line just there. So we can see A is 1 unit away, C is 1 unit away. A common error, students sometimes do this, not as badly, but you must have these equidistant. Again, if you're standing in a mirror 1 metre away, your face isn't slap bang straight in front of the mirror, it's 1 metre the other side. So all we need to do is name this line. Well, if we look at it, this point here is 2, 0, this is 2, 1, this is 2, 2, this is 2, 3, this is 2, 4. What we can see on each of these is that the x coordinate is 2. This is the line x is equal to 2. X is equal to 2, x is equal to 5, x is equal to negative 1 are vertical lines through that x coordinate. The lines y equals 1, y equals 5, y equals negative 3 are horizontal lines through the points where y is equal to, for example, 1 or y is equal to 5. So this now is our mirror line, and we can say now the single transformation that maps shape A to shape C is a reflection. Don't say it's being mirrored or flipped, it's a reflection in the line. So in the line now x is equal to 2. Need to be very, very clear with that. Okay, let's take that off. Let's do, so A to D, A to D. Okay, so A to D is just there. Well, that mirror line goes just there. This is the line y is equal to 1. Again, if you're struggling with y is equal to y is equal to 1, this is 0, 1, this is 1, 1, this is 2, 1, this is 3, 1, this is 4, 1. All of the y coordinates on that line are equal to 1. So this is the line y is equal to 1. So we would simply state now the single transformation that maps shape A to shape D is a reflection in the line y is equal to 1. You might want to look at that as a rotation about this point. Again, it's easier to do it with tracing paper. My work with rotations isn't brilliant. I just don't naturally see them, but do see them if I've got tracing paper. But if you wanted to try it as a rotation, you could try the centre of rotation about 0, 1. So that's A to D. Right, A to E. Well, let's look at A to E. Well, the mirror line here, this one's slightly more challenging. The mirror line with A to E is going to be here. So with 1.5 units either side. Remember, don't plonk it, don't put that it's there. It isn't, because A is 2 units from that line and E is only 1 unit. So we could say this is a reflection in the line y is equal to 1/2 or 0.5. Don't put it there, it's just there. Just measure that distance, 1.5, 1.5. So A to E, or E to A, is a reflection in the line y is equal to 0.5. E to D, it's telling me that it's not a reflection. Quite clearly it's not a reflection. If it was a reflection, we'd have to have this part here, or we'd have to have this slanty bit come in across here. This is a translation, and it's a translation from E to D. It's going to be now on here 0, 1. If we were going for D to E, it would be a translation of 0, -1, because it would be moving down. So that is not a reflection. If you wanted to do B to C as a translation, that would be 4, 0 as a translation, and C to B, -4, 0. So those are now reflections. We need to state that it's a reflection, and we need to give now the equation of that mirror line, or the line of reflection. So where does it have symmetry? Finally, enlargements. Enlargements are the only one where the shape has changed size. That's the word I'm looking for. Change size. That's the whole idea. An enlargement can be bigger or smaller than its original. So just because it's got smaller doesn't mean that it's not an enlargement. So what we need to do is state fully the single transformation that maps A to B, A to C, B to A, and B to C. With this, we don't need to find a centre. That comes in a more advanced video. If you want to, I'll show you how to do it towards the end of this, but we're just considering now the scale factor. So let's look at A to B. Well, A to B, and we could write it like so, A to B, this is an enlargement. We can't state got bigger. It is an enlargement. You must use that word. Like we've used translation, like we use rotation, like we use reflection. You must use a technical term. So from A to B, all you do is take a side length and see. So this side length on A is going to be 1. This side length is going to be 2. B is twice as big as A. So on here we can say now scale factor, or SF, 2. If we look at A to C, again, we take now one of the sides. We can see that A is 1, C is 3. You could, of course, have taken that one right here, which is 2. And this one, of course, is going to give us on here 6. So we can say now that the single transformation that maps A to C is an enlargement, and the scale factor, so enlargement, SF, 3. It's 3 times bigger. So scale factor is equal to 3. Right, B to A. Again, B to A, let's go back to A to B. It's still an enlargement. That doesn't matter that it's got smaller. It's an enlargement, but the scale factor this time is 1/2. A is half the size of B. We'd have to multiply all of the side lengths of B by 1/2 to get A. If we look at B, now this one's quite nice. What we've not done is C to A. C to A would be a scale factor enlargement of 1/3. B to C is quite nice. If we go from B to C, we're going from 2 to 3, or 4 to 6. So we'd say the single transformation that maps B to C is an enlargement scale factor now of 1.5. We'd have to multiply 1.5 by, or 2 by 1.5 to get 3. We'd have to multiply 4 by the 1.5 to get 6. So it doesn't always have to be an integer, a whole number scale factor. So that's what we do. Okay, right. So that's essentially the basic video over. I'm going to extend this slightly, just to show you how to do a centre of enlargement. So what we might do, let's do A to B. If you were asked to find the centre of enlargement for A to B, what you would do is draw guidelines. Hopefully this will work on this particular. Hopefully I won't go off the screen. So if you need to find the centre, what you do is go through the vertices of these, like so, and you find the corresponding points. So what we can say then is the single transformation that maps shape A to B is an enlargement, scale factor of 2, remember this is A to B rather than B to A, about the point -1, 3. The centre of enlargement on this is going to be -1, 3. So let's just put that there. That is -1, 3. So there we go. So we can see that all of those lines pass through this point right here. And once you draw those guidelines, that will give you the centre of enlargement. There is a video dedicated to this, but I thought I may as well include it for completeness. Because again, some students want to think that the centre of enlargement is going to be somewhere here, but it isn't. It's simply where we draw the guidelines. Look at this point and this point. That line goes through these two corresponding points. This point and this point, line through there. This point and this point, the vertices of these, draw the guidelines, and it will take you to the centre. This is not required on the course lower down, but it will be the further you go up. So let's just go back and look at what we've learned. 4 different types of transformations: translations, rotations, reflections, enlargements. When you're asked to state fully a single transformation, that's suggesting that you can use either one. Well, not all of them, because obviously an enlargement, it'd be obvious if it wasn't an enlargement. Or if it was an enlargement, it'd be a scale factor of 1. If it's a translation, it's simply moved. You state its translation and you state the vector by which it's moved. If it's a rotation, it's turned about a point. You state it's a rotation, centre of rotation or point of rotation, direction of rotation, and angle of rotation. If it's a reflection, it's been mirrored, it's been flipped in a line. You state it's a reflection and you state the equation of the line of reflection or the line of symmetry. An enlargement, you simply say it's an enlargement, it's got bigger, and you write down the scale factor. So there we go, a basic introduction to naming simple transformations.